Hello and welcome back to Dynamic System Modeling. In today's session, we will be covering the inverse Laplace transform. We noticed from previous sessions that we can obtain the differential equation of dynamical systems. For instance, if we obtain the second order differential equation of a mechanical system, assumed like this, then the ultimate objective behind this equation is to determine the response, either for the position, the velocity, or something else, and analyze the response in order to know which type of controls you need to apply. So let's assume in this case our objective is to reach x of t in order to look over its response. However, using the Laplace transform, we were able to determine x of s from previous sessions. And now we can apply the inverse Laplace to x of s in order to obtain x of t. And actually using this method of obtaining x of t is easier than deploying the traditional methods of solving differential equations in order to obtain x of t. So let's assume that we have or we obtained x of s, the Laplace function. Alright, and as you can see, it is a rational function. You need this rational function to be strictly a proper rational function. And I mean that the m must be less than n in order to deploy the method of partial fraction. However, if this is not the case, I mean m is greater than or equal to n, you need to deploy the long division. Then you can obtain a strictly or proper strictly rational function in which you can again apply the partial fraction method. Now let's take the scenario where the order of the polynomial in the numerator is strictly less than that of the denominator. Okay? And that the denominator can be factorized into two distinct poles. Then you can use the method of partial fraction expansion by saying a over s plus 1 plus p over s plus 4, right? Now we want to determine those two constants a and b. So you may use to have like a s plus 4 plus p s plus 1 over s plus 1 s plus 4. Then you cancel this term with this term and you reduce this equation. Then you determine the coefficient of the s and compare it with -1, and the rest you compare it with 5 and you determine a and b. To me it's easier to use it directly, so I say a equal to f of s multiplied by s plus 1 at s minus 1. So if we multiply f of s by s plus 1, we end up with minus s plus 5, s plus 4, solved at s minus 1, which is equal to 1 plus 5 plus 4, which is 3, 2. b, it is f of s. We multiply this s plus 4 directly by the f of s and solve for s equal -4. Okay, so we get minus s plus 5 over s plus 1 s minus 4, which is 9 over 3, and we end up with 3. Alright, so we determine the coefficients a and b. Now, so f of s is equal to 2 over s plus 1 plus 3 over s plus 4. Now we can determine f of t, right? So in order to obtain f of t, we need to perform the inverse Laplace of f of s. So we can use the table, okay? So we look over 2 over s plus 1. This is what we have. In order to obtain the inverse Laplace, we go in the opposite direction. It is e power minus 80, right? So we can write it down. 1 over s plus 8. Inverse Laplace, it is e power minus 80. Great. So f of t, the inverse of this term, it is 2 e power a minus 80. Okay, minus t 1 plus 3 e power minus 4 t. So that's how we obtain the time domain from the s domain. Now assume that you have repeated poles, okay, in which you have s plus 2 double the solution. What we will do again, so we assume this exists 2 times, so it is a over s plus 2 squared plus b over s plus 2 plus c over s plus 5. A is equal, we multiply s plus 2 squared by this, and we end up with 5s plus 16 over s plus 5 at s minus 2. Great. And b, it is derived from this part, right? So we can derive directly this term. So it is actually d by ds of f of s multiplied by s plus 2 squared. Okay? So it is the derivative of this term. So 5s, okay, solved of course at s minus 2, plus 16 over s plus 5, the derivative, solved at s minus 2, it is 5. And c can be determined by f of s multiplied by s plus 5 at s minus 5, which is 5 minus 5 plus 16 over minus 5 plus 2 squared. Okay, so now we can find the inverse Laplace of this term, which is given by this one. Okay, so let me write it down. F of t, so a is equal to 2. The inverse of s 1 over s plus 2 squared is t e power minus 2t, and b we have it plus 1, plus, again from the table you can see it is equal to e power minus 2t, c minus 1 e power minus 5t. Great. What if we have a complex pole? Again, what I mean, if you want to factorize this term, delta is equal to p squared minus 4ac. It is 4 minus 4, 1, 5, which is equal to minus 16, and this is negative. So you need to convert this into factorize it into in a complex format, right? However, you can do it, okay, you can do complex factorization. However, I prefer to convert it into something similar to the table, which is 4s plus 8, Okay, now I can factorize this. Okay, this is s squared plus 2s. I can make this as 1 plus 4. Okay, then s squared plus 2s plus 1 is s plus 1 squared plus 4, right? Then I can factorize the upper term, which is 4s plus 1 plus 4. So I change the 8 into 4 plus 4. Then I take the comma between those two terms. We obtain 4s plus 1 plus 4 over s squared, s plus 1 squared over 4, which is 2 squared, right? Now we get 4 s plus 1 over s plus 1 squared over plus t squared plus 4 over s plus 1 squared plus 2 squared. So this 4 is 2 squared, right? Now looking over the table, we can find that the inverse of s plus 1, this one, okay, it is e power minus at cosine omega t. So 4 e power minus t, because the exponent is 1, plus omega cosine omega t, which is 2, minus t sine 2t. Okay, this is f of t for sure. It is not a strictly proper rational function. Okay, as in this scenario we have the polynomial of order 2 up and down, right? They are equal. So we need to deploy the long division. In order to do so, we divide it using the usual division we know it. So 2s squared, we take the highest term, 2s squared divided by s squared, it is 2. 2 times s squared, it is 2s squared. 2 times 3, it is 6s plus 4. Then we subtract this from this. 7s minus 6s, it is s. 8 minus 4, it is 4. So the division of this, then 2s squared plus 7s plus 8 over this term is equal to 2. So the division is equal to 2. And we have a remainder of s plus 4 divided by this term. Now we can apply the partial fraction method, right? So we want to factorize this term. We can get delta, which is equal to 1, right? Then s12 is equal to minus b plus minus radical delta over 2a. So the b is equal to 3. Now we use the method we discussed previously, a over s plus 1, partial fractions, b s plus 2. We determine a. We multiply s plus 1 by this, s plus 4 over s plus 2. We substitute minus 1, 3 over 1, which is 3, and b is equal to s plus 4 over s plus 1 at s minus 2, which is 2 over minus 1 minus 2. Great. So now we can use the table again. We have f of s is equal to, let's substitute a by 3 and b by minus 2. Now we want to determine f of t. So the inverse Laplace of the constant is an impulse. Okay, so 2 delta t, which is the impulse function, plus 3 over s plus 1 plus 3. S plus 1, it is e power minus at minus 2 e power minus 2t. So this is the answer. Great, and thank you.